Okay, let's get started here. This is lecture 10, and this is 10A because we're going to do the first part of the lecture, and then the second part will be titled lecture 10B. Let's get the settings right here. So get these both going. Okay, and so I'm going to talk to you. We're beginning our section on open channel hydraulics, and so part 10A is going to encompass this part of the lecture here. And then, so this is all 10A. And then this part here will be part 10B. And we'll do that next. So you can watch them. And so I'm going to start off with giving you some kind of opening definitions and set the stage sort of for flow characterization before we get into concepts of conservation of mass and conservation of energy and those kind of things. The first thing, just kind of state the obvious here, or hopefully it's obvious, is we're going to be talking about volumetric flow, and we're going to use the abbreviation Q, which is fairly common in fluid mechanics and water resources publications. And so the volumetric flux of water is termed the flow, and so instead of talking about volumetric flow or volumetric flux, we just term it flow. We designate it Q, and the units are length cube per time. And so in English units, that'd be feet cube per second, or we also call it CFS. In British metric units, it's meters cubed per second. So when we talk about open channels, we have to make sure we understand what we're talking about, and we contrast it with pressure flow. Most of you in fluids are, most of you, or all of you have had to have fluids, so most of the time in CE 230, or I'm sorry, 3330, we've dealt with pipe flow, and that pipe has been flowing full under pressure. In the open channel world, we're going to be talking about flow where the surface of the flow is open to the atmosphere. And we also term that free surface flow at times. So you'll hear that used interchangeably, free surface flow and open channel flow. Now, I want to make mention that in a pipe, you can actually have open channel flow. It's just that the surface of the flow has to be vented to the atmosphere. So if it's in contact with the top of the pipe, it can't be under pressure. It has to not be pushing up against the top of the pipe. It has to have atmospheric pressure at the top, or otherwise it's not an open channel flow. Now, you'll notice that at times in sewer design, be that storm sewer or sanitary sewers, those function as an open channel. And so you should be aware of that as we think about things of sewer design, sanitary, storm sewers, those kind of things. So if we look at geometric elements, what we're talking about there is the issues of characterizing the cross-sectional geometry. So if we look at, this is a channel, and this is the fixed bed here. We've got a water surface up here. And so if we look at the cross-sectional area, that is deemed A. The wetted perimeter is a lineal distance that designates the interface between the fixed non-moving surface and the moving water. And so in this case, it's this very bottom of the channel here. That is a value of P. We can talk about the top width. That's the top width there. And so we have this idea of hydraulic radius, which is not really measurable, but computed from elements that are. And that hydraulic radius is defined as the cross-sectional area divided by the wetted perimeter. One that I don't have on the slide here, which is very important, is hydraulic depth. That's used quite a bit, and that hydraulic depth is designated D. You have to be very careful. Sometimes we'll designate the regular depth as D in terms of the depth of the flow, but hydraulic depth has a specific definition. It is the area divided by the top width. Okay, so T is equal to the top width. As we look at geometric elements, this is a table out of Chow's 1959 Open Channel Hydraulics textbook, and you can see that if we have a regular section like a rectangle or a trapezoid, this is a rectangle, you can see triangles, circles like a pipe, parabola, other kinds of shapes. This table here gives you the equations for the geometric elements. So if you've got area, wetted perimeter, hydraulic radius, top width, the hydraulic depth, section factor, that's an old term that we have for some things that we do prior to computers. They used to think about section factors when they were doing design things and had these design tables and design graphs. But now we compute them directly. So we really don't worry about a section factor too much. But as you can see here, the area is the width, V, times the depth, Y. For a rectangle. For a trapezoid, it's the bottom of the trapezoid, the bottom width, that's the B, and the sides are the side slopes, and that has run over rise. I'm sorry, not run over rise, but it's the Z is down here. So if it has 2-to-1 side slopes that we talk about in geotechnical engineering or in river engineering, we talk about 2-to-1 side slopes. We're not talking about 2 on the rise to 1. In terms of that'd be very steep, but 2-to-1 side slopes are 2 horizontal for every 1 vertical. So the Z here, you can see that for area, we've got B plus Z, Y, and then times the Y. That's the area equation for a trapezoid. You can find a handout inside module 10 that will give you this, and much better, I've got it into a Word document so you can see it a lot cleaner. It's not, this is photocopied, scanned right out of the Chow's textbook, and so I've got one that we've created that's a little easier to read. So I would suggest that you have this handy when you take quizzes, because I'll give you fairly standard geometries to do various computations for. So it's very handy to have the geometric elements. If we look at velocity, that's a measure where it has units of length per time. And we'll express it in this class either in feet per second or meters per second. It's variable throughout the cross section. It's not constant. And so we have this graph down here. You can see we're in the vertical. We've got the velocity going from 0 at the bed up to some value near the surface. This is what's called a no slip condition on the velocity assumption here, that the area right, or the location right where the bed and the water surface intersect, at that location, the velocity is 0. We talk about that as a no-slip condition. When we talk about velocity distribution, we're characterizing the velocity field. In this case, we're talking about a vertical velocity distribution, but we could also be talking about longitudinally across the cross section. Here we've got in the vertical, we've got the higher velocities are near the surface, the farther away we are from the bed of the river. We also would have some sort of velocity distribution across the channel, going from where probably the velocities are the highest over to where near the bank where they're going to be the lowest. And so in our computations in hydraulic analysis, we typically use the mean or average velocity in our analysis. So we have to go through and we calculate the mean velocity, which is the discharge or the flow rate divided by the cross-sectional area. And typically you'll see me, I'll put an overbar on the velocity just to designate that that's a mean value. And one of the things we're going to do is, because we use the mean velocity a lot, we have to put correction factors in for that. And so when we look at the velocity head, which we're going to talk about in a second with the energy equation, we have the mean velocity used, and that's not an exact or an accurate representation sometimes of the kinetic energy. So we end up putting in a Coriolis coefficient or a velocity correction coefficient that basically allows us to still use the mean velocity and correct for it using the alpha. So if we go further into actual flow characterization, we can talk about steady versus unsteady. And in that situation, we're talking about flows at a point and where the change with respect to time of any derivative or any variable you want is equal to 0. So if we're at a point and we talk about the velocity change with respect to time, that'd be 0 if it's steady flow. The depth change with respect to time is equal to 0. So you can see that that steady flow is talking about at a point in the location. And so if any of those variables change with time, the condition of unsteady flow exists. Now, I want to make sure that you understand that this is at a point. We're not talking about spatial coordinates, whereas if I'm going, if this is the bottom of my river and I'm flowing downstream, I'm not talking about the velocity at this location is going to equal the velocity at that location. That's a spatial kind of thing. And so that may or may not be true, but when we're talking about steady, we're talking about at the same point, looking at any changes over time. And in this case, we're looking at velocity, and as long as that velocity does not change with respect to time at that location, or the depth with respect to time doesn't change, that is considered a steady flow. Now, when we talk about velocity, we have to deal with turbulence, and so we know that turbulence is a perturbation or a fluctuation of that velocity. I'm not talking about that. We're averaging over lengths of time, and so the average of the velocity over some time is not changing. Where you might have some fluctuation either side of the mean velocity, that's not what we're talking about here when we're talking about steady versus unsteady flow. Now, this is a hydrograph. We spell it like this. It's from the U.S. Geological Survey stream gauging station, Salt Creek at Western Springs, Illinois. That's in the Chicago suburbs. And you can see that we've got time on the x-axis, and we've got stage, which is a kind of a measure of the water surface elevation. And so you can look at this point in time here, the stage is relatively constant. And so we would call this a steady flow period. Whereas when you have some rainfall, in this particular case, occurs, and then the hydrograph, the stage changes, this would be an unsteady period for the flow. If we talk about further looking at flow characterization, we've got this concept of uniform versus non-uniform. And so when we talk about uniform flow, we're talking spatially. And so we're talking about what is the change with respect to distance of a certain variable. And if that's equal to 0, that change with respect to distance, we would call that a uniform flow. And in that situation, we would say that the velocity change with respect to distance is 0. The depth with respect to distance is equal to 0. One thing I want to note is here we've got depth. This is actual depth of the water. We could also have designated it Y. That's also one common way to refer to depth. Don't confuse this necessarily with hydraulic depth. Just want to call that to your attention, which is area divided by top width. That's not what we're talking about here. This is just regular depth. And so when we talk about uniform versus non-uniform, if this is not true, this is a non-uniform flow, which means that the velocity with respect to distance is changing, the depth with respect to distance is changing. That's what we're talking about. That's the typical case in most rivers you see, is you have water flowing down a river system, and because the channel is irregular, it's got gravel in the bed, so there's areas where it's very shallow, you get a ripple, you get areas where it's very deep, you get a pool, and you can see that the depths are changing with respect to distance. That is a non-uniform flow. The majority of what we deal with is non-uniform. The case of uniform flow has some advantages in terms of some of our analysis. We'll actually assume uniform flow at times and compute certain things, and it helps us with our hydraulic analysis. One thing I want to mention is this definition here of prismatic channel. Prismatic channel is simply saying cross-section geometry, slope, and roughness do not change with respect to distance. So if you start out at a rectangle at one point, it's still a rectangle of the same shape and size as we move downstream. All right, further as we go to uniform versus non-uniform flow, we can see here that this is the bed of the channel, and this is the water surface here, and so we've got some slope, and if this is a uniform flow, that would mean that the depth does not change with respect to time, with respect to distance. So this depth here is going to be the same as this depth. So that means that the water surface slope is the same as the bed slope. And then if we look at the total energy grade line, This is the total energy at this point. This is my kinetic energy here. That, if it's uniform, it's the same downstream. So that means that my friction slope, which again, the friction slope is just if this is L, this distance here is L. The friction slope is basically the head loss divided by distance, where the bed slope is going to be the change in the bed elevation with respect divided by the distance. And so you can see how those all align there. And if we have uniform flow, the bed slope is equal to water surface slope, which is equal to friction slope. And again, uniform, basically the change in the velocity with respect to x is 0, the change in depth with respect to x is equal to 0 in that uniform case. If I've got non-uniform flow, you can see down here below what happens. There we've got the change of the velocity with respect to x is not equal to 0, nor is the depth of water. And so we're going to be talking about this. This is going to be something that when we talk about non-uniform flow, we're going to solve some problems dealing with that. This is the common situation out there in the rivers that you're going to deal with. If we look at conservation of mass, this is a major equation or a concept that we're going to use in open channel hydraulics. And so conservation of mass is also known as the continuity equation. But let's look at it from control volume theory. If I look at a system right here, which I've got right here, and you can see that if I look at what the Reynolds transport theorem, which says, okay, look at an extensive property of the system. If I break that into control volumes, because the system is large to work with, so in fluid mechanics, we use control volume theory. And so if I've got this control volume here that's shown by this dotted line, if I look at that and look at control volume theory, I can say that the change of the extensive property, whatever it would be, of the system with respect to time is equal to the change of the extensive property in the control volume with respect to time plus the net flux. And so you can see here we've got a flux of that extensive property. In this case, I'm sorry, it's the density times the intensive property, which is the extensive property divided by the mass, which allows us to look at what the flux parameter is. So this is a flow rate volumetrically, and the rho times B is sort of what the mass flux of that extensive property would be. And then so this is on the downstream side of it. So this is what's passing out of the control volume. This is what's coming into the control volume. This is the in, this is the out. And so the difference between the two is the net flux of that extensive property. Now, we've got intensive property, which is this little b, so that shows up here, shows up there. Now, if we're going to be dealing with mass or conservation of mass, our extensive property in this situation is going to be mass. And so then if we've got mass being our extensive property, if I calculate little b, that's just basically mass divided by mass, or it's equal to 1. And so I can rearrange that and say, okay, the change of the mass of the system with respect to time is equal to the change of the mass in the control volume plus the net flux change of the mass as it fluxes across the control volume boundaries. Now, if I've got a system of mass, we've heard that matter cannot be created or destroyed, so you've got mass is what it's there. It's what we've got. So the system mass is equal to 0. And then if we've got steady flow, we've got no change of the mass in the control volume with respect to time, because what comes in goes out. And then we're left with the flux. And so we've got this, the net flux going across the boundary. Further, if we look and we say that we've got incompressible flow, okay? So if we've got incompressible flow, and that means that the density of the fluid does not change from one location to the other, you simply get rid of these terms, and you have basically left with the area and the velocity term. And so we know that's the flow rate, and you can see that the mass flux is equal to this. We get rid of the density terms, we end up with that the flow rate is equal to A1V1 equal A2V2. So for steady, incompressible flow, we end up using this concept all the time. We call this the continuity equation. All right. Now, as we move through, we've got continuity in our pocket as one of the tools we're going to use. The next thing we want to use is the energy equation. Now, in fluid mechanics that you learned, you dealt with mainly pipe flow. The energy equation you remember seeing is something that looks like this: alpha 1 V1 squared over 2G plus P1 over gamma plus Z1 is equal to alpha 2 V2 squared over 2G plus P2 over gamma plus Z2 plus the head loss term. And then if you've got a pump or a turbine, you'd have to account for that as well. Now, notice the difference here. Everything is the same except for this pressure term. And we, as I defined earlier, we don't have a pressurized flow here. We've got a flow that's vented to the atmosphere. There is a discussion in a bonus lecture. I called it 10A in the module 10. It's not the same thing as this 10A. It's just a development of the energy equation for open channels from the second law of thermodynamics. And so here we've got the form of the energy equation we're going to use for open channel flow. We're replacing the depth at each location for that concept of the pressure term, which we have in a pressurized flow pipe. All right, so if we look at that energy equation for uniform flow, remember what we defined as uniform flow: the derivative with respect to distance is equal to 0. So the depths don't change, the velocity doesn't change no matter where you're at. So you can start getting rid of terms because y in is going to be equal to y out, and the velocity head in is equal to velocity head out. So all we're left with is our bed elevation term of the upstream end or the inside, the location where the flow is in, and the flow is out is the bed elevation there plus the head loss term. So that's all we've got left. If we divide through by the distance L, which is L is the distance from one to the other, from location in versus out, we end up showing that the change in the bed elevation by the distance, well, what is that? That's simply the bed slope. And if we've got the head loss divided by L, what is that? That's simply this friction slope, right? So this is my bed slope, there's the friction slope. So we show, once again, that for uniform flow, the bed slope is equal to the friction slope. This is going to be a very important concept for you to remember, that for uniform flow this is true, because we're going to exploit this when we work on some of our problems, because we're going to need to know, even though we don't experience uniform flow in nature very much, we use that as sort of a base to help us understand hydraulically what's going on with the system. Okay, so this is just further showing these out here. I'm going to end lecture 10A right now, and you can come back after you've watched this and look at lecture 10B.